Hey there and welcome. So, have you ever looked at a chemical name and just thought it was a complete, random jumble of letters and numbers? Well, you've definitely come to the right place. We are going to crack the code on the language of chemistry and show you that there's actually a simple, beautiful logic behind it all. All right, let's start with the one idea that changes everything. Think of it this way. A chemical name isn't just a bunch of jargon. It's a super precise, detailed address for a molecule. I mean, just like your home address tells someone the country, the city, the street, and the house number, a chemical name tells a chemist every single piece of a molecule and exactly where it's located. So, to really see how this works, let's grab a name that looks kind of complicated on the surface. We're going to break it down piece by piece, and I think you're going to see that once you know the rules, it's not intimidating at all. Actually, it's surprisingly logical. Okay, we're going to start with the absolute core of the name. See that butane part right in the middle? That's kind of like our street name. In chemistry, this tells us the length of the main carbon chain. And but always means a chain of 4 carbon atoms. That's the backbone of our molecule right there. Next, let's jump all the way to the end of the name. See that all tacked on? That's like telling us what kind of building is at this address. It signals a special feature, what we call a functional group. And in this case, all is a dead giveaway that there's an alcohol group, an oxygen and a hydrogen, stuck somewhere on that chain. And finally, let's look at the very beginning. 3-chloro. This is the house number and tells us what's sitting on the front porch. It tells us 2 things. Chloro means there's a chlorine atom, and that number 3, that tells us exactly where it is, on the 3rd carbon atom of our 4-carbon chain. A perfect, precise location. So when you put it all together, you realize 3-chlorobutanol isn't random at all. It's basically a set of instructions, a blueprint that says, hey, start with a 4-carbon chain, go ahead and add an alcohol group to it, and then attach a chlorine atom specifically to carbon number 3. Every single part has a job to do. Okay, so now that you've seen the logic in action, let's pull back the curtain and look at the universal formula that makes all these names work. This is the official blueprint that chemists use to build or read literally any chemical name, no matter how simple or crazy complex it looks. Every single one of these names is built from 3 core parts. Right in the middle, you've got the word root. That tells us the length of the main carbon chain. That was our butane. At the very end is the suffix, which tells us about the bonds and the main feature, the functional group. That was our all. And then at the very beginning is the prefix, which describes any branches or other things attached. That was our 3-chloro. All right, let's build a name from the ground up, starting with the most fundamental part, the backbone of the molecule. This all comes down to the word root, which, simply put, just tells us how many carbons are in the longest continuous chain. That's it. And this right here is the basic vocabulary you've got to know. 1 carbon is meth, 2 is eth, 3 is prop, 4 is but, just like in our example, and 5 is pent. Think pentagon. This is the absolute foundation for every single name we're going to build. Okay, so we've got our main street. But what happens when you have little side streets or cul-de-sacs branching off? In chemistry, we call these branches or substituents, and there are 2 really simple rules we follow to make sure we name them correctly every time. Rule number 1 is the longest chain rule. Your first job always is to find the longest continuous path of carbons you possibly can. Now, it can be really tempting to just follow the straight line, but if making a turn gives you a longer chain, then that becomes your main chain. Like in this example, the correct path actually has 5 carbons, not just the 4 you see in a straight line. So once you've found that longest chain, you need to give every carbon in it an address, a number. And this brings us right to rule 2, the lowest number rule. The whole goal here is to number that chain so that any branches attached to it get the lowest possible address number. Let's see this in action. We've got our molecule, and we've found the 4-carbon main chain, which makes it a butane. Now look at that little branch. It's just a single carbon, so we call it a methyl group. If we number the main chain starting from the right, that methyl group ends up on carbon number 3. But is that the best we can do? Nope. What if we try numbering from the other direction, from left to right? Suddenly, that same methyl group lands on carbon number 2, and since 2 is lower than 3, that's the winner. The key takeaway is simple. The lowest number for the branch always wins. That makes the correct name for this molecule 2-methylbutane. And now for the final and I'd say most important piece of the puzzle, the functional groups. These are those special features on a molecule like the alcohol group we saw earlier. You should think of them as the VIPs of the chemical world. They get priority treatment when it comes to the naming. So how does that priority work? Well, it's a pretty simple hierarchy. The functional groups, our VIPs, get the top spot. When you're numbering your carbon chain, your number one goal is to give that functional group the lowest possible number. Any regular old branches are totally secondary. They just get whatever number is left over after the VIP is taken care of. And what's really cool is that these VIPs actually change the ending of the name. An alcohol group, the OH, changes the suffix to -al. An aldehyde gives you the suffix -al, and a ketone gets -one. The presence of one of these powerful groups completely dictates the last part of the chemical's name. And really, that's it. The longest chain rule, the lowest number rule, and giving priority to the functional groups. With that simple blueprint, prefix, word root, and suffix, you now have the fundamental tools to read and understand this incredibly logical, structured language of chemistry. So I'm going to leave you with a little challenge. Now that you can see this whole thing is a system of logic, not just a bunch of random words, what's the most complicated chemical name you can find and try to decode? Go on, give it a shot. I think you might just surprise yourself with what you can figure out.